What I want to look at in this video is calculating the inverse of a 2 by 2 matrix. Now this comes from the fact that we're starting to look at more properties of 2 by 2 matrices and more calculations and operations that we can do with them. And it comes from the existence of several special matrices which are part of our 2 by 2 matrix system and are associated with multiplication and addition with regards to matrices themselves. Now under addition, a set of 2 by 2 matrices has an identity matrix given by O equals 0, 0, 0, 0. Now this is because any generic matrix A, B, C, D, add this identity element, is the equivalent of taking the identity element and adding that generic matrix, which will give me a solution of the generic matrix itself. So it has an identity matrix that gives me this. Each matrix A, so again we'll stick with that generic one, also has an additive inverse which is given by negative A. So in this case, negative A, negative B, negative C, negative D. And this comes from the fact that if we think of adding matrices together, if we have A and we add the negative of A, that gives us this identity element O. So it'll give us a matrix consisting of just zeros. So it has an additive inverse there. Now if we think of multiplication, a set of 2 by 2 matrices has an identity element. This is given by the identity matrix, which has 1s in the diagonal and 0s in the other diagonal going from left to right. Now this comes from the fact that if we take any generic matrix in 2 by 2, so again our A, B, C, D, and multiply it by this identity matrix, that would be the equivalent of taking the identity matrix and multiplying it by the generic matrix, and we would always get the solution of our generic matrix. So there exists elements where we're able to combine them with matrices, and regardless of the order we combine them when addition and multiplication is used, we get back to a generic matrix. And for addition, we've got an additive inverse. So the question is begged, do we have a multiplicative inverse? So is there a matrix given by PQRS such that if I multiplied my generic matrix A, so given by the ABCD, by this matrix PQRS, I'd get the equivalent of multiplying the matrix PQRS by my generic matrix A, and the solution it would give me is the identity matrix. So does this multiplicative inverse exist? That's the question that we want to know. And the answer to that question is quite simple. Yes, it does. The inverse does exist. So the multiplicative inverse of a matrix does exist. Now, I could go through a massive proof to do with it. However, what I'm going to do here is I'm just going to state it and I'm going to tell you how we can work with it. Now, the multiplicative inverse of a matrix A, so given by A to the minus 1, what that is that's going to be given by 1 over AD minus BC times the matrix D minus B minus C and A. But we have to put a condition on this, that AD minus BC cannot be equal to 0. So this is the inverse for, again, our generic matrix A, which is equal to ABCD. So this here is the inverse of that matrix. Now again, I've highlighted it there too. I'm going to keep highlighting it, that property has to be true. The AD minus BC cannot be equal to 0. One thing to note, AD minus BC is a determinant. So essentially what I've said to you is that the determinant of A cannot be equal to 0, and if it's not equal to 0, the inverse exists. If it is equal to 0, we have no inverse for that matrix, so the multiplicative inverse, A minus 1, does not exist for that matrix. So here's an example for you that I want to work through, and I'll just show you the steps to doing it. Then I'm going to tell you a few properties associated with this. So I need to remember the formula, A to the minus 1, so inverse is 1 over AD minus BC, and then that's times the matrix given by D minus B minus C A. Now the first thing to do is line this up with your matrix A to get the values for A, B, C and D. So we know this is all based on the fact we've got a matrix A which is equal to A, B, C, D here. And I'll line up the values. So from this I can say that A is 2, B is 4, C is 1, and D is 3. First thing to check is AD minus BC. If that's 0, we can't go any further. So AD minus BC, so the determinant of our matrix, that's equivalent in this one of 2 times 3, take away 4 times 1. So that's the equivalent of 6 minus 4, which is 2. Great. AD minus BC is equal to 2. We can get the inverse of it. So what we now do is substitute the values into the formula. So my inverse is equal to 1 over AD minus BC. Well, we know that's equal to 2. So it's going to be a half. And then it's just substituting the values in. So D is 3. I've got negative B, which is negative 4. I've got negative C, which is negative 1. And I've got A in the bottom corner, which is 2. So I can just leave it like that. If you wanted to get the fraction inside, I could take it in, and I'd end up with 3 over 2, negative 2, negative a half, and 1. So there you go, that is the inverse of this matrix here. Key things you need to make sure you do are the steps that I've shown you here. Equate the ABCD and make sure you get the right values, and then check this. Check the determinant in the AD minus BC. There's no point in going any further if you don't check that first, because if it's equal to 0, there is no inverse. Check it's non-zero. Once we've got that, we can go for it. Then it's a case of substituting in the formula and simplifying when you can. The inverse of a 2 by 2 matrix is fairly straightforward to calculate. We just have to remember the steps and remember the formula. Now, there's a couple of properties I want to highlight here associated with the inverse of a matrix that we need to also bear in mind just in case they pop up. So the first thing is just the formula. So I've just written that down again, that the inverse of a 2 by 2 matrix, A, which is given by ABCD, is given by A to minus 1 equals 1 over AD minus BC times the matrix D minus B minus C, A. Now one thing to note is that the matrix D minus B minus CA, that's called the adjoint or adjugate of A. And this is denoted by ADJ of A, just as you see written here. So what we can then do is simplify the formula, and you may see this written down a few times, into this, that the inverse is equal to the adjoint matrix of A divided by the determinant of A. Because remember, as we highlighted before, this is just the formula for the determinant. So again, that's another quick and easy way to remember it. Going back to the point that we mentioned before about the determinant, if the determinant is equal to 0, the inverse is undefined. This is what's called a singular matrix. If it has no inverse, it's called singular. If the determinant is non-zero, it's non-singular and invertible, so we can calculate an inverse. As I mentioned, that is always the first thing you check. Make sure it's non-singular and invertible for you to be able to do the inverse. Now, a couple of things to remind yourself about for a pair of 2 by 2 matrices A and B when it comes to associating them with inverses. First thing being that if A squared equals KA plus BI, so written from previously, what we can do is rearrange that, and we can write the inverse of A as being 1 over B times the matrix A, take away K over B times I, the identity matrix. Now the K and the B both come from the formula for A squared there. So they both come from this formula there. And to join on to that, if A is orthogonal, then A to the minus 1 is 2. So another thing you may discover from working through the formula for that is that if A is an orthogonal matrix, the inverse of A is as well. Now if we have S, which is a skew-symmetric matrix, then the identity matrix plus S is non-singular, and A, which can be given by I minus S, I plus S, that is orthogonal. So we're able to do that, and if we've got an orthogonal matrix here for this, if we calculate the inverse of that, which we know we can because they're non-singular, our inverse is also going to be orthogonal. If we've got our matrix A being symmetric, and our B being another generic matrix, then B times A times the inverse of B is also a symmetric matrix. So combining those two matrices in that format, if A is symmetric, so is the solution to that. And if A and B are both symmetric, what we can also say is that AB minus BA is a skew-symmetric matrix. So it's skew-symmetric around the diagonal. We also know that we have the property that if we do the inverse and then we calculate the transpose of that matrix, that's the equivalent then of taking the transpose of the original matrix and calculating the inverse of that. Therefore, if A is symmetric and invertible, then the inverse is symmetric as well. Now again, let's go back to our two generic matrices A and B. If A and B are both invertible, then the inverse of A plus the inverse of B is the equivalent of the inverse of A times the matrix given by A plus B, then multiplied by the inverse of B. So again, another little formula for you to work with. And if we have a symmetric matrix, of order n by n, this has at most a half n bracket n plus 1 distinct elements within it. Yeah, so these are distinct. They may be repeated elements, but these are at most the number of distinct elements. And if we've got a skew-symmetric matrix of the same order, it has at most a half n bracket n minus 1 distinct elements associated with it. So again, that just comes from the shape and the symmetry within the matrix due to those properties. Final thing to remember about the inverse is if we do the matrix A times B and then take the inverse of it, that's the equivalent of doing the inverse of B times the inverse of A. So it's not just then doing the inverse of A times the inverse of B. That's not the way it works. We have to revert it around the other way and do the inverse of B times the inverse of A. And the determinant of A times B is the equivalent of the determinant of A times the determinant of B. That feeds into why this is the case. So a lot of information thrown at you there. There's a lot of key things that you need to remember and be able to work with when it comes to calculating the inverse of a matrix in 2 by 2. But one of the biggest parts, as I've obviously mentioned, is the formula. Remember that formula. You'll be able to calculate the determinant of any 2 by 2 matrix that I can throw at you and answer questions associated with them. So for example, when does the inverse not exist? You may get questions along those lines. You have to be able to answer them and use the properties that I've just described to you, particularly determinant not being 0, in order to be able to answer questions associated with the inverse of a 2 by 2 matrix.